Hello everyone and welcome to my talk entitled An Introduction to Process Simulation using FactSage. In this presentation, we'll show you how to use FactSage in order to simulate process from an overall mass and energy perspective. It all starts with a process. You see here the schematics of a technology called an electric arc furnace. This technology is used to melt scrap and also to refine direct reduction iron. After adding some energy to the system via the electric arc that are produced, we can melt the scrap. You see here that different phases might be in equilibrium in this technology. So the slag phase and the molten metal are typically encountered in this type of reactor. The idea under the process simulation using computational thermochemistry is first to be able to identify what are the operating conditions of the simulated process, in this case in terms of temperature, pressure, and mass balance. Of course, we need some precise knowledge about the technology to know if there are some local equilibria that can establish. This will have an impact on the imposed constraint that we add to our system when performing our thermodynamic calculation. With that, we'll be able to simulate the process and obtain the resolved mass and energy balance. These balances are important because they can provide, for example, the partitioning of elements in different phases. So, for example, the chromium partition between the molten metal and the slag phase. It can identify the principal and parasitic reaction as well as their environmental impact in terms of quantification of gaseous emission. We can also resolve the energy balance, which is pretty useful when we're doing process design and optimization. Finally, you can see on the right the equivalence of all these concepts integrated into the FactSage interface. Here are the basic ingredients that you need when you want to successfully simulate a process using computational thermochemistry. Like we've just mentioned, it is important to be able to identify all the imposed conditions to the system. We also need to have an accurate thermodynamic description of each important phase of the system. That could be compounds or solution phases. This is where the FactSage software is so useful because we have specialized databases for different primary metal production. Then we need an integration of all the important components in these solutions of importance, such as the slag phase. This is critical if one wants to be able to quantify the partitioning of different elements inside various phases. Then we need to make an adequate phase selection in order finally to be able to interpret and analyze the result obtained from these thermodynamic calculations. So we'll be able to generate graphs and process some data. Our latest scientific contribution on the topic of process simulation is presented here. This manuscript entitled On the Application of the FactSage Thermochemical Software and Databases in Materials Science and Pyrometallurgy will show you how to simulate different fundamental experiments as well as processes. You see here TGA simulation using open mode calculation in FactSage, DSC simulation, and finally process simulation, in this case the Holyrood process. Enjoy your reading. So to come back to our FactSage mini workshop, we're going to define the objectives of this first workshop session. So the first objective is to be able to introduce some basic options that are available in FactSage, such as the database selection, the identification of the initial condition, adiabatic calculation, precipitation and formation target options, impose activity constraint, as well as the construction of streams. The second objective is to define some fundamental process simulation concepts that are essential when we're analyzing pyrometallurgical processes, such as the Boudouard reaction, the oxidation of impurity using oxygen blowing, as well as the slag reduction using carbon. Finally, we'll show you how to analyze the result that we obtain in terms of chemistry of the different phases that are in equilibrium, as well as the overall phase assemblage for some imposed conditions. We see here the 6 examples that we're going to cover during this first workshop session. The first example will show you how to evaluate the Gibbs free energy of a compound as a function of temperature. Example number 2 will show you the analysis of the methane combustion that we can do in FactSage under different type of conditions. Example number 3 will show you how to quantify the volatilization of zinc during the melting of some scrap materials. In example number 4, we're going to talk about stability and metastability of phases, namely graphite and cementite in the iron-carbon system. In example number 5, we're going to talk about the Boudouard reaction and its impact on the imposed PO2 inside a reduction furnace. Finally, the example number 6 will talk about oxygen blowing in molten iron to get rid of carbon, as well as the slag reduction when we over-oxidize the iron and produce some slag phase that we want to recover partially. Enjoy! In this first example, we're going to show you how to use the equilibrium module to plot the evolution of the Gibbs free energy of a compound as function of temperature. It has to be remembered that all the thermodynamic properties of these compounds can be found in the compound module, which is presented here on the left. To get the thermodynamic information of a compound, you only have to write its chemical formula here. There are several options in the compound module, so you can view the list of product. In this case, all the combination of elements that you will enter in the chemical formula will be fine for each database. Here is an example, so let's work on the Al3Li compound. So Al3Li, by clicking on Enter, you can find all the databases that contain information for aluminum and lithium. And you see here the FTLite database, which contains thermodynamic information about a lot of intermetallic phases for the aluminum industry or for light metal materials. You see here that the Al3Li phase is available. If you click on the phase, you can see some information like its molecular weight, its name, and the reference where you can find the thermodynamic information that is stored in this database. If you click on the plus button, you will see the different allotrope of this intermetallic. You can click on them and see a little bit more of information here. If you go back to view and you enable the extended properties, you'll be able to see the thermal expansion parameters that are used to define this property, as well as other characteristics. At the top of this menu, you can see the enthalpy of formation of this compound, in this case, which is equal to minus 29,800 joule, the S298, and by, again, clicking on the little plus here, you can see the CP expression for different range of temperature. These are the basic ingredients that you need in order to generate the Gibbs free energy of a compound as a function of temperature. Let's go now in equilibrium and try to see how this Gibbs free energy of this compound evolves as function of temperature. So basically, the first step here is to enter the mass balance that you want to work with. In this case, I would like to work with 1 mole of Al3Li. So this is what I'm going to do, Al3Li. I don't need the initial condition in this case. I want to see the evolution of the absolute Gibbs free energy as a function of temperature. So I'm going to unselect these initial conditions, and I'm going to look at the database that are now activated in equilibrium. What I want to do is to work with the FTLite database. So I'm going to select this database, and usually you'll have selected the FactPS database, which contain all the thermodynamic information of the gaseous species in your system, plus a lot of other thermodynamic information about other compounds that can form in a given system. You see here that I've mentioned previously that I would like to work on a molar basis, so I can just double click on the unit here and modify the unit. So I want to work in mole and degrees Celsius. In the next menu, you'll be asked to select the phases that you want to consider in your calculation. In this case, I only want to look at the evolution of the Gibbs energy of a specific phase, which is the Al3Li intermetallic, where the thermodynamic information is stored in the FTLi database. So I'm going to right-click on the pure solid here and select the phase that I'm interested in. In this case, the Al3Li. We've mentioned previously that we had several allotropes, so I'm going to work specifically with the L12 crystal structure in this case. And click on OK. So now I'm almost ready to calculate the Gibbs free energy of this specific phase as a function of temperature. The last step to do is to enter the range of temperature that I want to work on. So let's say in this case, I want to go from room temperature, so 25 degrees Celsius, up to a temperature of 600 degrees Celsius per step of 10 degrees Celsius. You see now that FactSage will calculate 58 calculation, and by clicking on the calculate button, you'll obtain all these results. So here are the calculations for each temperature. The last thing that you can do with these calculations is to plot the Gibbs free energy as a function of temperature. So this is what I'm going to do in a moment. So here in output, I can plot some results. And what I'm interested in is to evaluate the Gibbs free energy. So the y-axis will be the Gibbs energy as a function of temperature. And by doing that, you'll see that you can get the evolution of the Gibbs free energy as a function of temperature. In this example, we're going to see different scenarios where we burn methane in order to release some energy, for example, to heat some system. Starting from the previous calculation, we can start a new equilibrium calculation by clicking on this button here on the left. When you click on this button, you will be asked if you want to clear the current system, which is what I want to do right now. So it also asks if we want to keep the selection of databases that we already have. In this case, we have activated the FTLite as well as the FactPS database. In this case, I'm going to say no, and I'm going to only select the FactPS database. Again, it has to be remembered that the FactPS database contains thermodynamic information about gaseous species as well as compounds. So I want to see what happens when I react some quantity of methane with air. So this is the first reaction that I'm going to analyze. I'm going to put CH4, and we'll add some reactant. So I'm going to add two reactants, basically O2 and N2. What I will do now is also to vary the proportion of methane to air that I will have in my system. And the way to do that is to introduce the alpha parameter. So in this case, I'm going to add in here 0.21 alpha of O2, 0.79 alpha of N2, and I'm going to add 1 minus alpha mole of CH4 in my system. In this case, I'm really curious about the variation of enthalpy of my system. Therefore, I need to activate the initial condition button. When you activate this button, you see that you need to define the initial condition of each stream that you introduce in your equilibrium calculation. In this case, we only have one stream, which implies that when I'm going to modify, for example, the temperature of the methane, it will modify the temperature of all the other species that I have here. I'm going to work in this case with reactants that are at room temperature and at a pressure of 1 bar. Everything is set now for a first calculation where I want to see how many energy or how many enthalpy is released upon the combustion of methane by air. So I'm going to click on the next button. Going there, you see that there's no solution that are available in this case because I'm working solely with the FactPS database. And by left-clicking on my mouse, I can select all the gaseous species that are considered in the FactPS database. I can select as well all the pure solid and all the pure liquid. You can look at the phase selection by right-clicking on the plus button. By doing that, you can see that the FactPS database contains a lot of gaseous species. So you have here H, H2, and if you go down, you'll see O2, CO, CO2, etc. We're almost ready to run our first calculation. So what I'll do is to impose the temperature of my system to be 25 degrees Celsius and vary my alpha parameter from 0 to 1 per step of 0.01 to see the energy that will be released upon the combustion of methane by my air. By doing that, so if I run these calculations, I will obtain 100 and more calculations. So here are the results I'm getting. So if we look, for example, at an alpha different from 0, you see that you have the following output. So you see the initial condition in terms of temperature, pressure, and volume of my system, and you can see what happened in the gas phase. So there are some chemical reaction, and you can see the dominant species of my system. So you have CH4, N2, H2O, etc. So if you scroll down, you'll be able to see the other phases that might form upon the chemical reaction. What is also really important is to look at the delta H of this reaction, which is highlighted here at the moment. This is interesting. We can see how this delta H evolves as a function of the ratio between methane and air. So we can plot this result by doing the following procedure. So we're going on output, plot result. And what I want to see now is the evolution of the delta H of my chemical reaction as a function of the alpha parameter. So I'm going on axis, and I'm going to plot the delta H as a function of my alpha parameter. And if I plot, I'll get the following curve. So you see here, when you have an alpha equal to 0 or 1, that no chemical reaction occurred. Therefore, the delta H is equal to 0. And you can see on this graph that there is an alpha parameter that maximizes the delta H, or the heat release, upon this combustion. So this is the first example, and we can now close this window. The other example that I want to work with you is to see the adiabatic flame temperature for the system. So we can go back to our mass balance here. In fact, we don't need to go here because we don't change anything in terms of mass balance. So we're going to go to the next window and work, not in this case at an imposed temperature, but for an imposed delta H. This implies that all the energy that will be released upon the combustion of methane will be used to heat the product. By doing so, we'll be able to evaluate the temperature of our system as a function of the alpha parameter. So if we click on calculate, we'll obtain our result, and we'll be able to see how the temperature of my system evolves as a function of the alpha parameter. Again, we can look at the output and see the species that are present in my gas phase and the thermodynamic properties that we obtain as a function of the thermodynamic calculation that is performed using FactSage. So we can again output our results. So in this case, we want to plot the evolution of the temperature of our system. So in axis, we want to see the temperature as a function of our alpha parameters. By doing that, we see that we maximize the temperature of our system when we have an alpha parameter close to 0.9, which brings a temperature of about 1957 degrees Celsius. In this example, I want to show the volatility of some species when you increase the temperature of a system. This could be critical, for example, when you're using an electric arc furnace and you want to recycle, for example, some scrap material that contains, for example, zinc. The first thing I'll do is to enter a 100-gram basis of stainless steel that contains some impurity. In this case, I'll put copper zinc, and carbon as the impurities. So the first step to do is always to check the database that are activated. So if you go in data search, you can see that at the moment I have the FactPS as well as the FSTL database that are activated. This is exactly what I want. Like I've just mentioned, we want to work on a 100-gram basis. So we have the right unit, so we're going to work in gram, and I'm going to add some reactant. First element that I'm going to add is chromium. So I just mentioned that I want to work on a stainless steel. So I'm going to put about 13 grams of chromium. And in this case, chromium is added to form an oxide layer at the top of the stainless steel to protect the material from the corrosion caused by the surrounding. When you want to have a stainless steel with good mechanical property, you also add nickel. So I'm going to put 4 grams of nickel. And nickel typically will stabilize the austenite phase, and therefore you're going to be able to reach optimum mechanical properties. In terms of impurity, I just mentioned that I want to have 0.3 gram of copper. I want to add also a little bit of carbon, so 0.2 gram of carbon. And finally, I want to add 0.5 gram of zinc, which would be present in our system. For example, let's say that you have other scrap that contains some galvanized steel, so therefore you have a contamination with zinc. And finally, you can add the rest of the mass balance to iron. So I'm going to put iron, and there's an option in FactSage, so you can click on question mark 100, and this will evaluate the rest of the 100-gram basis to obtain your overall mass balance. So we're ready in terms of mass balance. We don't need to activate the initial condition because mostly what we want to check at this point is, like I've mentioned, the volatility of zinc. And we can click on next. You see now in this panel that there are a lot of phases that can be selected, so a lot of solution, pure solid, liquid, and gaseous species. I'll start with the solution. You can select all the FSTL phases that are there. You see, for example, the liquid phase, the FCC, so austenite, the BCC phase, so ferrite, etc. You can also left-click on the gas, liquid, and solid to activate all these pure compounds. If you right-click on the plus button, you will see the phase selection that the software has done for you. It's important to see here in this phase selection that cementite is present. Even though it is a metastable, we'll see later on that we can customize our phase selection so that this phase can appear. Because as you probably know, graphite would be the equilibrium phase when we give enough time to our system to reach full equilibrium. Okay, so I want to define a temperature at which I'm going to melt everything. So typically an electric arc furnace should work around 1600 degrees Celsius at a pressure of 1 bar. And I'll do one single calculation. I'm hoping to melt all the metal, and this is what you see here. So I have a 100-gram basis, and I have a 100 gram of liquid metal that contains all my elements. And at the top of our result menu, you can see the chemistry of the gas phase. And without any surprise, you see that zinc has a fugacity that is really close to 1, which means that the gaseous vapor is close to form. A common mistake is to think that there will be no gas release since there's zero amount in this case, which is not the case in reality, because typically you will have an atmosphere surrounding your system. Therefore, the liquid phase will be able to equilibrate with this gas phase, and in this case, will be able to transfer a lot of zinc. Another important point to see here is that the fugacity is equal, in fact, to the partial pressure in this case, since we have an ideal gas solution. Okay, if you want to see how the zinc would be transferred if we have an atmosphere surrounding our system, I'll add a small amount of argon to my system and see what happens. We can go back to our mass balance menu and add another reactant, in this case, argon. We know that argon is not reactive, so I'm just going to put an arbitrary amount of 1e minus 3 gram of argon and see what is the impact on the phase assemblage that I'm calculating using FactSage. If you do one calculation, you'll see that zinc now is an important species in the gas phase. It has been transferred. You see its fugacity that is really close to what we saw previously. The slight difference is coming from the fact that you have a non-negligible amount in your gas phase, and you cannot exactly reach the fugacity that was obtained previously, but it's clear now that zinc has been transferred to our gas phase. This is potentially problematic because this gas phase can be condensed in cooler zone of your system and can lead to an attack of the refractory material by this zinc vapor. In this example, I want to show how to define a metastable equilibrium by putting phases dormant. The ideal scenario or the ideal case study is the iron-carbon system. In this case, the saturation of carbon in iron is defined by the precipitation of graphite under equilibrium condition. However, we know from the experience that cementite is the metastable phase that form under real-life condition. So what I'll do is to show you how to define this equilibrium. I'll start by looking at the databases that are activated, and again, you see in this case that the FactPS as well as the FSTIL databases are activated. I'm going to work with the following mass balance. So I'll start by adding carbon, in this case 0.5 gram of carbon and 99.5 gram of iron. We don't need to activate the initial condition as we want to analyze the phase assemblage for a particular condition of equilibrium. We'll click on next and you'll see the phases that are available for the calculation. One has to remember that we require to activate or select all these phases so that we consider them in the calculation. I'm going to manually activate the solution, so the liquid solution, FCC and BCC. I'm going to left click to activate the gaseous species, the pure liquid, as well as the pure solid. The first calculation I'll do is at a temperature of 600 degrees Celsius. So in this case, we want to see if first we've reached carbon saturation with the mass balance I put, and then identify which phase is the phase that saturates the iron solid solution. So if I click on calculate, I'll be able to analyze the result I obtained. And in this case, you see that at 600 degrees Celsius, ferrite would be the stable solution for our system. And if we scroll down, we see that carbon graphite has precipitated, which means that we've reached saturation, and we can, by looking at this output, define what is the amount of carbon that we have in our BCC solid solution. And this value is presented by the zone I'm just highlighting. If we scroll down, we can look at the activity of all the other phases that were selected but are not present in our phase assemblage. And I'd like to highlight here cementite, which has an activity of about 0.5, therefore it is not a stable phase. Many metallurgists will mention that cementite should be the phase that we observe under a lot of different synthesis conditions or heat treatment conditions. In this case, what I want to do is put graphite dormant and see how it impacts the solubility of carbon that I have in my system. So I can go back to the phase selection and do a couple of modifications. So you can right click on the plus button for the pure solids, and you can decide to put some phases dormant. What I'll do here is to put carbon, graphite, and diamond as metastable or dormant phase. So I'm going to right-click on the plus button and put this phase dormant. I'll do the same thing, for diamond. I'll put it as a dormant phase. So now the software will consider these carbon allotropes in the calculation, but will not allow them to precipitate or form in our phase equilibrium. The interesting thing here is that we'll be able to see the activity of these allotropes. We can do OK and re-evaluate the equilibrium state of our system. You see now that, again, we have our BCC solid solution that contains carbon, which is now saturated by cementite. And if you remember the result that you obtained previously, you'll see that we have a slight modification in terms of carbon solubility, which makes sense since cementite is a metastable phase when compared to graphite, for example. Another interesting thing here is if you look at the activity of graphite, you have this symbol here to emphasis on the fact that graphite is a dormant phase. You see that its activity is greater than 1, which means that it should be considered in the phase assemblage because you cannot reach an activity greater than 1 if the phases are in equilibrium. In this next example, we're going to study a really important equilibrium state, which is induced by the Boudouard reaction. In this case, we have an excess of carbon that reacts with oxygen, and we impose the partial pressure of oxygen in our system. This chemical equilibrium is super important for the design of pyrometallurgical processes, as it allows to identify if we can reach conditions for the reduction of a given oxide. The first thing I'll do is to see the evolution of the chemistry of the gas phase when you work in an excess of carbon. So the first thing I'll do is enter the reactant for this reaction. I'm going to add O2, so I'm going to work on 1 mole basis of O2, and I'm going to add a second reactant, which will be the carbon. In this case, I want to work with an excess of carbon, so I'll put 4 moles of carbon. The next step is to ensure that all the right databases have been selected. So by clicking on Data Search, I can see what are the databases that are selected at the moment. For now, I only want to work with the FactPS database. This database contains all the thermodynamic information about the gaseous species as well as pure compounds. Since I'm not interested in the variation of the state properties like enthalpy, I do not need to activate the initial conditions option. The next menu is the one where you can select all the phases in your system. So by left-clicking on this square, you can select all the gaseous species as well as all the pure solid. If you right-click on the plus button, you'll be able to see what are the gaseous species that are considered in this equilibrium calculation. You see here that we have 12 species. Same thing for the pure solid. So if I right-click on pure solid, I can see the different allotropes of carbon. So you have graphite and diamond. I'm now ready to impose the condition for the equilibrium calculation. So I'll start from room temperature, so 25 degrees Celsius, up to a temperature of 1200 degrees Celsius per step of 10. So I'll do 118 calculation. What I want to focus on next will be the evolution of the dominant species in my gas phase as a function of temperature. We know from the Boudouard reaction that at low temperature we should have a CO2-rich gas, and at high temperature a CO-rich gas, which ultimately allows us to reduce oxide. In between, there is a shift which should occur at around 700 degrees Celsius. I can now calculate these equilibrium states, and you obtain all these results. So as expected, when you're at room temperature, you see that in an excess of carbon, so in this case, my excess of carbon is graphite, you have a gas that contains mostly CO2. If I go to the maximum temperature by going in Show Pages, Go To, and we go to the last to highlight the result at 1200 degrees Celsius, you see that we shifted the composition of the gas up to a value of CO of almost 1 bar. So it's a CO-rich gas that can be used for the reduction. Again, we have an excess of carbon. In terms of partial pressure of oxygen, we can see here that we have a fugacity of 7.55 10 to the minus 18, and I'm going to keep this value as I will use it in future calculation to see if we can reduce or not a given oxide with this imposed partial pressure of oxygen. So the first thing I'll do is to plot the evolution of the dominant species in my gas as a function of temperature. To do that, I will go in Output, Plot, and plot results. So now what I want to see is the evolution in terms of molar fraction of the dominant species as function of temperature. So I'm going to click on Next. I'm going to select my variable, so I want to see the molar fraction as a function of temperature, and to refresh the min and max value, I just have to click here. Now I'm almost ready. I need to select or activate the species that I want to plot on my graph, and to do that I'll use this select option and browse in this menu to select the dominant species that I want to study. So I'll select CO2 and CO. For now, there's no point in selecting the O2 because with the scale that I'm going to use and the fact that O2 is virtually equal to 0 in terms of partial pressure, I won't see its behavior. So I can click on OK and plot the results. So now you see that you have an evolution of a gas phase that contains mostly CO2 up to a gas phase that contains mostly CO at higher temperature with a shift around 700 degrees Celsius, which is predicted by the Boudouard reaction. That's great. Now I want to focus on the evolution of the partial pressure of oxygen as a function of temperature. In this case, I will have to change the axis of my graph so I can see something. I'm going to close this window and go back to my axis. Like I've mentioned previously, we go up to a value of about 7.55 10 to the minus 18. So what I'll do now, I'm going to add a maximum value of 10 to the minus 17, and I'm going to tick every one e to the minus 18. So now I'll be able to see the behavior of the partial pressure of oxygen as a function of temperature in my system. Next is to select specifically my O2 chemical species in the gas phase. So this is what I'm doing right now. And I can now plot the results. And what I can see here is the evolution of the partial pressure of oxygen as a function of temperature. At 1200 degrees Celsius, you can double click on the line on this graph, and you can go see the exact value, which again is 7.55 10 to the minus 18. Great. So we've seen that the partial pressure of oxygen start to increase drastically or exponentially above 700 degrees Celsius. So we can close these windows and go back to the mass balance. So now the other example that I want to show in this example is the imposition of a partial pressure of oxygen to see if I can reduce a given oxide. To do that, I'm going to remove the carbon because I know now what will be the partial pressure of oxygen imposed by the Boudouard reaction. So when I have an excess of carbon, and I'm going to introduce some hematite, Fe2O3. The idea now is to see if with this imposed partial pressure, I can obtain metallic iron. So what I'll do, I will go in data search and activate the FT oxide database as well as the FS steel database. So now I can have access to all the phases that are obtained in terms of metallic phases and in terms of oxide phases. The next strategy is to perform this calculation at a high temperature. So we've mentioned 1200 degrees Celsius before, and I'll impose the partial pressure of oxygen I asked you to record, which was 7.55 10 to the minus 18. The first thing I'll do is to deselect everything and to perform again my phase selection. So what I can do, I can start with the solution and select all the solutions that are available. So I can either select by specific database or select all the solutions. This is what happened. I can left click on the gaseous species, pure liquid, as well as the pure solid. So now all my phase selection is done, and I can go specifically in the gas phase and impose the partial pressure of oxygen. To do that, I right-click on the plus button, and I again right-click on the plus button of the O2 species. Now you have this menu that is popping up, and you can go directly to the activity and impose the activity of 7.55 E minus 18. This will represent the partial pressure of oxygen that you get when you have an excess of carbon in your system, therefore imposing the partial pressure of your reactor. And I'm almost ready to perform my last calculation, so I'm going to go at 1200 degrees Celsius, and I'm now ready to do the calculation. You'll see here that the mass balance in this case is not relevant, as FactSage will try to identify an equilibrium state that respects the constraint of the partial pressure of oxygen that I've imposed a few minutes ago. So by clicking on Calculate, I can now see the result at 1200 degrees Celsius and look at the phases that are in equilibrium to see if I can or not obtain metallic iron. And it is indeed the case. So if you look at this output, you see that you have iron FCC that is produced. So that's great. It means that with this low partial pressure of oxygen, I'm able to obtain metallic iron. In this example, I want to show you how to manipulate streams, so save stream and manipulate them in subsequent calculation. The example I picked is the oxidation of a liquid metal, in this case iron, that contains some amount of carbon. Again, this is a really important example in pyrometallurgical applications, as it is often the case that you want to remove some impurities by blowing oxygen, so to oxidize some impurity. In this case, you have to be careful because too much oxygen blowing will lead to the oxidation of the metal that you want to value, in this case iron. So to speed up the presentation, I'm going to open a simulation that I've already saved on my computer. So by clicking on Open, you can open pre-existing example. So here, the example of interest, WS 2020, example number 6. By double-clicking on the file name, the software will ask if I really want to clear the current system and open this new calculation, and I'm going to say yes. And this is the window that you obtain. I'll go back to the mass balance and explain to you this example. So I have 99 grams of iron, and I added 1 gram of carbon, just to mimic the fact that some impurities are present in my liquid system when I impose a sufficiently high temperature. I also have an alpha parameter to introduce oxygen in order to mimic oxygen blowing in my application. By clicking on Next, you can see all the phase selection that I've done. So all the solution coming both from FS steel and FT oxide are selected. I've also selected all the gaseous species that are contained in my gas solution here, as well as all the pure compound. It is also important to mention here that I did not select the pure liquid, as the important pure liquids are typically component of the solution that I've already selected. So for now, I will keep this pure liquid without any selection. The first calculation I want to do is to confirm the temperature that I've imposed, so 1600 degrees Celsius, to be an adequate temperature for my furnace. So what I'll do is a precipitation target on the liquid to ensure that at this temperature, all the system will be in the liquid state when I'm not blowing any oxygen. So I'm going to put an alpha of 0 for now. Like I've mentioned, if I put a precipitation target on the liquid, I'll be able to evaluate at which temperature all my system is liquid. So you can right-click on the eye here and get the option of precipitate target phase. If I do that, I'll be able to identify what is the temperature at which I only have liquid and I start to form a first solid. So you see here that the primary phase in this case would be the FCC solid, and it has an activity of 1. So it is about to form, and its amount is equal to 0. So therefore, this temperature here at the top, 1461.7, is the liquidus temperature. I can go back to the phase selection and do a similar calculation, but this time for the formation target. In this case, I'll be able to evaluate the solidus of my system. That is, the temperature above which you start to form a liquid. This temperature can also be super important for different pyrometallurgical applications, as you may know that the formation of a liquid might lead to some sticking in some part of the process that perhaps you don't want to happen. So if I put my F option and I calculate, I see a lower temperature here, which is supposed to be my solidus. So looking at the phase equilibrium, so I have my FCC iron, and you will see that the activity of the liquid metal is equal to 1. So it is about to form. And therefore, I have the solidus of my system. So it is safe to say that if I were at 1600 degrees Celsius, all my system will be in the liquid state, at least when I'm not blowing any oxygen. The idea now is to blow oxygen and see how it's going to impact the amount of carbon that I have in my liquid metal. So I'll put back the mass balance that I had before. So I'm going to go from 0 to 3 per step of 0.05. So I'll do 61 calculation. And the objective here is to see the evolution of the carbon content as well as the oxygen content inside the liquid metal. And I'll run these calculations. Basically, if everything was fine, I should see a decrease in the amount of carbon in the liquid solution, as well as an increase in the oxygen content, because there is a dependency between the dissolved oxygen and carbon in the liquid metal. And to see that or visual that, I'm going to use the output option. So I'm going to output, plot the results. And what I want to see is the weight percent of these elements inside my liquid metal. So I'm going to go in axes. I want to vary the weight percent of the species from 0 to 1 per step of 0.1. And I'm going to use an alpha parameter going from 0 to 3 per step of 0.05. Okay. The only step now that remains is to select the component of the solution that I want to observe, which are oxygen and carbon in the liquid solution. So I'm going to go here and select, and I'm going to go in the solution that I want to work with. So I'm going to clear everything and select the carbon and oxygen from the liquid solution and click on OK. So now, by plotting these results, I should be able to see the evolution of the carbon content in the liquid metal as well as the oxygen content. And as expected, you can see that as I am blowing oxygen, I'm decreasing the carbon content of my liquid iron. However, at the same time, I'm increasing the oxygen content inside the liquid metal. And what happened at this point, I'll show you with the phase assemblage, is that we start to produce a slag phase. So at this point, I oxidize too much my system, and I will start to lose some iron in a slag phase. So I'm going to close this and show you this other calculation. So now instead of plotting the weight percent of species in a solution, I'm going to plot the amount in gram of different phases in my system. So I click on OK. And now what I want is to select. At the end, you will see the solution. So I want to select the liquid and the slag phase. Now I can see that I have a lot of liquid, and I start to form a slag phase around 1.770 in terms of oxygen blowing. What I'll try to do next is to save the stream at an alpha value of 3 for the slag and try to see if I can reduce again this slag by injecting carbon inside of this slag solution. So I'm going to close this window. I'll go back to my result window and go in show pages, and I will go to the last calculation at alpha is equal to 3. In this case, like we've just mentioned, I have the presence of a slag phase that contains FeO mostly and Fe2O3. So what I want to do next is to save this stream and try to use it in a subsequent calculation in order to see if I can reduce the slag by injecting carbon. So to do that, I need to save this as a stream. The way to do that is to go in output, stream file, save stream file, save solution, and I want to save the slag. So FT oxide slag number 1. I'll give it a name, so it's slag number 1 for our example 6. Okay. So now I have the stream, I can reuse it in a new equilibrium calculation. So this is what I'll do in a moment. So I will generate a new equilibrium calculation. Yes, I'm going to keep the same database selection that I had previously. And now I'm going to incorporate this stream by doing the following task. I'll start by edit, mixture and stream, import a stream, and now I'm going to import the slag that I've just saved. So slag 1, example 6. By doing that, you see that FactSage introduced the slag 1 with 100% of in terms of mass balance, which is about 5.68 grams. To that, I'm going to add carbon to try to reduce the slag phase. And I'm going to put, an alpha amount of carbon. This is good. And now I can reselect all the important gas species, solid, and solution. So FS steel and FT oxide are the database or the solution that I want to activate. Again, I'll use my alpha parameter from 0 to 3 at a temperature of 1600 degrees Celsius, and I'm going to perform 61 calculation. Now, what I want to see is how the phase assemblage is evolving as we are adding carbon in my system. To do that, again, we've seen that previously. I'm going to go in output, plot, and I'm going to plot the results. And what I want to see in axis is the amount of gram as a function of the alpha parameter. That's okay. And the phases that I'm interested in are the liquid metal and the slag. So I'm going to select the liquid as well as the slag phase. And finally, by doing that, you can see that you can recover all the iron that you would have in this slag as you inject carbon in your system. So I know that at an alpha parameter equal to 1.5, I will have recovered all the iron that was oxidized in the slag phase. So that's it for the first part of our mini FactSage workshop. I hope that you enjoyed this presentation. And let's see now how my students use FactSage in their applications. So thank you so much for your attention.